to us about tractability in a simple overparametrized model.
Okay, thanks to the organizer. So what I'll talk about is a paper that we are finishing writing and hopefully will be on archive next week or something like that with Yichao Zhang and Kangje Zhou. And okay, let me start with an appetizer that is an interesting geometric question, and is the following. So even if I am not interested in statistics, this is an interesting math question. You have I-eddy Gaussian vectors in Rd, n of them, and out of them you construct a polytope, a random polytope. So this is defined as the set of vector theta in Rd, such that xi theta is less or equal than 1 for all i's. Okay, so the picture is that you have Rd, of course, and then you cut it with planes, half spaces, and then you look at the intersection of all of these. Each of these half space contains the origin. So this is non-empty. And so this is my set. And the natural question is, what is the radius of this set? Okay, so the radius is of course the maximum norm of any, the maximum L2 norm of any vector in this set. And okay, a corollary of the theorem that I'll state a little bit later in this talk is the following. With positive probability, so let's take n and d going to infinity with n over d going to some number delta. And one thing that we can prove is that with positive probability, and I can describe in a minute what this means precisely, if you want, the radius of this set is what? Well, of course, more and more hyperplane means smaller and smaller radius. The set is, monotonically decreasing, and it turns out that it's decreasing quite slowly. Is 1 over square root of 2 log delta plus small o in delta of 1 over log delta. Okay, and precisely, to be more precise, this means that the limit of the probability that the radius of END is bigger or equal than 1 over square root 2 log delta plus epsilon over log delta. There is an epsilon of delta going to 0 such that this limit and d going to infinity, this limit is equal to 0, and the limit with the minus and less or equal is less or equal than a constant less than 1. Okay, so on one side is a high probability bound, and on the other side is a positive probability bound. Unfortunately, we don't have the tight threshold. The best known result about this geometric problem before our work was, there is a paper by Baldi and Vershinin actually of this year that proves that the probability that the radius of the same set is bigger than 1 plus epsilon over square root of 2 log delta is less or equal than e to the minus d. So it's only one side of these two bound, and is the epsilon is in front of the 1 over square root 2 log instead of that thing. Okay, so this is the geometric question. Let me tell you why I was interested in this problem. Actually, I discovered the connection with this more or less at the end. Yeah.
Did they prove that for a fixed positive epsilon, or is there some?
Yeah, for this is okay. So the precise statement is the following: that for any epsilon, for any epsilon, there exists C of epsilon, such that if I think n over d is bigger than C of epsilon, then this happens. Okay, and the nice thing is that it's non-asymptotic. They have an explicit error bound. Now, the way it's stated is slightly different. Okay, if you like geometry, there is a dual of this problem that is the following. Take n random points. There is another way of constructing a random polytope, right? You throw n point, and then you look at the convex envelope of this point, and then you look at the inner radius of this convex envelope, right? The inner radius means the radius of the largest ball that is contained inside. The relation is that one is the inverse of the other. And so they state the result for this one. Okay, so let me say, now that I stated one theorem, a word on motivation, why I am interested in this. I'm motivated of this because of machine learning, of statistics. So say that you have a supervised learning data problem with a parametric family. And the xi's are in RD. And perhaps you have a loss L that is R times R. To R equal to then 0. And okay, there is a lot of interesting. There has been a lot of interest over the last couple of years in interpolators. So what are interpolators? These are models that interpolate the data that is achieved zero loss. So okay, so here say that the vector of parameters is a p-dimensional vectors, and we are interested in what I call ERM0. So this is the set of vector of parameters such that L of yi, f of xi, and theta is equal to 0 for all I less than n. Okay. Okay, so of course, the loss, of course, we all know examples. Think of this, or classification loss. Okay, so if you start thinking of this problem, there are a couple of questions that you start. Okay, so why there is interest in this? Because many modern machine learning systems work by finding an interpolator. So not only minimizing the empirical risk, by finding a model that achieve nearly zero empirical risk. So there are two theory questions. One is, when is ERM0 not empty? Or three questions. Question 2, when can we find it in polytime? And question 3 is, what are its generalization properties? What are the generalization properties, in particular of the vector theta that is found in polytime? And these three questions have been studied in some detail for very simple losses. So studied for linear models. Namely, when f x theta is basically theta times x, and square loss. Okay. So this includes a special case, kernel methods, random feature methods, linear regression. And I wrote some papers about this. Peter wrote some papers, Sasha Raklin, others. Now, yeah, so it would be interesting to move beyond. So in this case of linear model, in particular, these first two questions are very easy because the set of interpolators, each of these constraints is a linear constraint. So constraint theta to stay on a affine space, and finding polytime is very easy by gradient descent, by convexity. Okay, so I want to study a little bit the simplest example, non-convex example. That has a little bit of structure, and the simplest non-convex example turns out, or I believe, is binary classification, linear binary classification. With the negative margin. So the bad aspect about this specific, the nice aspect is that there is some nice math. The bad aspect is that it's not a method that I would recommend to anybody for any practical classification problem. But perhaps the hope is that we gain some insight by studying this example, and then we can apply to other cases. So this is also known in starting with the physics literature as the negative perceptron. So what is this case? This case is simply the case in which my function is linear and my loss is 0 if y hat y is bigger or equal than kappa, and some positive quantity if y hat y is less than kappa. And here the caveat is that, so this is classification with a margin kappa. The important feature here is that the data will not be linearly separable, not linearly separable. So we cannot do usual max margin classification, and I'll take kappa negative. So in this case, what is the set of empirical risk minimizer, or the set of solutions, is the set of vector theta in the, so I have to normalize them in the unit sphere in d dimension such that yi xi theta is bigger or equal than kappa for all I. Okay. Let me now define something about the model under which I want to study this. So I will study this under, okay, I will take as I said before, ND going to infinity, n over d to delta. And I'll study two models, pure noise model. This means that the features will be normal 0 ID, and the labels are just random, uniform, if you want, plus minus 1, independent of the xi, and what we call linear signal model. And this xi normal 0 ID, and probability of yi equal plus 1 given xi is phi of xi times theta star for some vector theta star. And okay, so the assumption on the function phi is that phi has exponential tails. So phi of t goes like 1 plus 1 minus e to the minus alpha t plus smaller order terms as t goes to infinity, and e to the alpha t as t goes to plus smaller order term as t goes to minus infinity. And okay, and the two things that I'm interested in is, of course, okay, what I call delta S kappa. This is the, the satisfiability or the existence threshold. This is the sup of all delta, such that lim n d to infinity n over d to delta p of ERM 0 not empty is strictly positive, plus lim inf, and delta alg kappa is basically the same, but with the sup over delta such that there exists a polytime algorithm. So these are the two things ideally I would like to compute. And okay, so let me now briefly review what is previous work on this problem. And then state my result. So meanwhile, perhaps you can think if you have any question about the statement of the problem. While I erase this. Okay, any questions about the problem statement? So if I have to trace a figure, so let's do a figure, right? Perhaps this stimulates some question. What you have is that you have the sphere as d minus 1, and each one of these constraints here, or each one of these constraints here cut a spherical cap from this sphere. Okay, so I have a vector, and then I cut out a spherical cap. I cut out another spherical cap, cut out another spherical cap, and then I'm left with this kind of Swiss cheese shape, and I want to know whether the Swiss cheese shape is empty or not. This is equivalent to the polytope figure that I drew before. The equivalent picture is that you have a polytope, and I'm intersecting it to the unit ball, and then I'm interested in this region, this region, this region, everything that stays inside the polytope. Yeah, so the results that, we have some results about 3, but they're not. So I'll give the results about 1 and 2 that we have. I'll state some results about 1 and 2. In the paper, we have some results about 3, but.
Sorry, I thought the interpolators want to have the inner product be kappa or more.
Yeah. Yeah. So here YIXI is this, and so I'm cutting off anything that is less than kappa.
Kappa can be negative.
Kappa is negative. Data are not separable. Okay, so what is known? Of course, the case kappa equal positive has been studied for a while, since cover 96, 1965. Kappa equals 0. So what it proved is delta S at kappa equals 0 in my language is equal to 2. Elizabeth Gardner, using physics method 1988, using replica methods, computed delta S kappa for kappa positive. This was proved by Shrebina, Tirozzi, 2003, and by Stojnic. So Stojnic has a simpler proof based on Gaussian comparison, and then there is more recent papers, for instance, Emmanuel Candes and Pragyasur consider. So this is all with the random labels. So it's the pure noise case, and then there is results with linear signal. In my terminology, by Candes Sur and myself and Feng-Ruan, so on. Yeah, myself. In this case, of course, all of this is about delta S, and in this case, the problem is convex, so delta S is equal to delta algorithmic. All right, the case of kappa negative has received much less interest. So one notice here is that this proof implies that, okay, let me write it here. The proof of Stojnic also implies that a bound for kappa negative, so Stojnic 2013 implies that delta S of kappa is always upper bounded by what's called the replica symmetric formula. That is 1 over the expectation of kappa plus G positive part square, where G is a standard normal random variable. Okay, for kappa negative, this is much less studied. It's been studied quite a bit in physics since a work by Franz and Parisi, 2016, that studied it as a simple model for jamming. So this is using replicas. And I don't know of any other mathematical results apart from this Stojnic and a recent paper by Hamed El Alaoui and Mark Selke, that 2000 perhaps 20, that give an algorithm under the assumption that there is no overlap gap. Okay. Yeah. So question, Bush question. What does this paper do? This paper writes the full replica symmetry breaking formula, and yeah. So they claim that you need full replica symmetry breaking to achieve the thing, right? So and they compute. Then their main interest is really computing certain exponents of how this solution behaves as you move to the phase transition boundary. Okay, so perhaps so. Why zero not always because you want it on the sphere, right? Right. In the case in which kappa is positive, you can always move from the sphere to the full ball. Okay, so the problem is equivalent to a convex problem. In the case of kappa is negative, you cannot, if you have a solution of smaller norm, this doesn't satisfy the original problem. All right. Okay, so let me perhaps for comparison the replica symmetric formula, let me write for you how does this behave. This is, if you do this integral, this is what? Is 1 is phi kappa over kappa square over phi kappa times 1 plus mol of kappa of 1. Yeah? If you do this integral, where this is the Gaussian CDF. So phi kappa is the Gaussian CDF. And perhaps it's obvious, but the reason why this phi kappa appears is that, erase this. If I fix a vector theta, for a given vector theta, the probability that in the purely random model, say the probability that this is less than kappa, so the probability that the constraint is violated is exactly phi kappa. Right, so what is the naive calculation? The calculation is, if you give me a vector theta, what is the probability that it satisfies all the constraints? Is 1 minus phi kappa to the n. Each constraint is satisfied with probability 1 minus phi kappa to the n. Okay, how many vectors there are on the sphere? About e to the d. So you would expect that the right scale is e to the minus cd. When this happens, then there is the phase transition. So if you write it down, this means that so phi kappa must be quite small. So e to the minus n phi kappa, perhaps about e to the minus c times d. So you would expect that interesting stuff, interesting regime. Is delta of order 1 over phi kappa, roughly. So this explains this behavior 1 of phi kappa that you see in the replica symmetric bound, and you'll see in all the results that I'll state. Actually, now I'll state one theorem that collects all the things that I want to talk about. Okay, so I'll collect all the results that we have about questions 1 and 2. So for pure noise model, what we prove is that delta S of kappa is log kappa over phi kappa times 1 plus molo in kappa of 1, and delta alg of kappa is bigger or equal than 1 over phi kappa, 1 plus molo kappa of 1. So I'm taking, always in the definition of this, I already taken n and d going to infinity, and then we have formulas of bounds for each kappa, but this bounds becomes tight for kappa large. And for the linear signal, a very similar picture. Delta S of kappa is e to the alpha times kappa times log kappa divided by 4 phi kappa times 1 plus molo kappa of 1. Here in small o, the subscript is the asymptotic variable, and delta alg of kappa is e to the alpha kappa, and then there is 2 phi kappa, 1 plus molo kappa 1. So, okay. So what this tells us is that, okay, first of all, the replica symmetric bound is loose, is wrong by factor kappa square. And second, that we can pinpoint, at least for large kappa, the thing to the leading order. And third, that there is a large gap between what we can achieve algorithmically and the threshold, the existence threshold of solutions. Okay, so the picture is like this.
Signal cases.
Yeah, alpha times kappa. Yeah, alpha times kappa. Yeah. So these thresholds move up, of course, when there is a linear signal, because okay, the data are, so you want to separate the data. So in the linear signal, the data look more or less like this. So it's easier to separate them. Instead, if they are purely random, it's harder to separate. Okay, so this is the picture, right? Kappa, delta, and then this is replica symmetric, and the replica symmetric goes up formula. And now we know that the right threshold is somewhere down here. This is delta RS. And then that there exists an algorithmic threshold that is even lower. I mean, we don't know if it's lower, but we have a lower bound that is so lower than that. Yeah. Okay, so good question, excellent question, because this is the next thing that I want to describe. What is the algorithm? And I'm sorry for all the people that are smart at coming up with smart algorithms in this room. This is very stupid what I'm going to say. So let me take the pure noise case, or for simplicity, all the yi equal plus 1 is completely identical. And what is the idea? We want to solve what I want to solve. I want to maximize, ideally, theta subject to xi theta, let's say, bigger or equal than kappa for all I. Okay, so this is what I would like to do. If I find one solution that has norm bigger than 1, I won. Okay, this is equivalent to our problem, right? Okay, so we have this polytope, and we want to get something as far as possible from the origin, and we do something really stupid. We take a random vector and we maximize the linear function. Okay, and if you want the justification, okay, the justification, you can think of it like this. If you call this your objective function, you can think of linearizing the objective function around the random initialization and maximize this. Okay, where theta 0 equal v is, let's say, normal 0 or epsilon v, and v is normal 0 identity. All right? So you can think of this as starting at the random initialization and doing just one step of Frank-Wolf algorithm, if you are an optimization person. Okay, so again, so what we do is maximize b times theta subject to theta xi less or equal than kappa for all I. Okay? And now this is a convex program, and it's quite easy to, it's relatively easy to analyze precisely. Once you get, so this is a linear program. Once you get the linear programming solution, you come up, you construct an estimator just by normalizing. Okay, that satisfies a kappa margin solution by normalizing. So if the norm is at least 1, this is a margin solution. And the analysis says that if delta is below this threshold, or this threshold, depending on the model, then the norm will be bigger than 1 with high probability. This is the algorithm. Okay, so I think that's more or less all that I wanted to say. Perhaps let me say a couple of things about open questions here. Okay, let's say open questions. Okay, not naturally for this type of workshop, it would be interesting to figure out whether there is really a gap between delta alg and delta S and delta alg. This is actually something that I think can be done with existing techniques, or let me say in progress. There is another question is, if you look at the physics papers and you try to interpret them, the picture that I have in mind is that there is here a kind of point in which these three are, not like this, but the replica symmetric is always wrong, but at a certain point, these two thresholds coincide. There is some regime in which the two thresholds coincide, the algorithmic and the statistics, and then perhaps possibly they differ. So it would be interesting to understand this. So, okay, let's say sharp. Okay, two sharp threshold. We don't prove that it's a 0, 1, and then in the sense of a sharp threshold, in the sense that exists in the sense of concentration, and 3, full replica symmetry breaking formula. Let's say 4, existence of a region of kappa, with delta alg equal delta S. Okay. So this is perhaps in order of difficulty nearly.
Evidence is there for one?
What kind of evidence there is for one? No, very little, but I think it should be possible to do the overlap gap calculation, and I suspect that it gives what it should be. But okay, we didn't yet. We don't have any results that I can quote on this yet. Okay, that's all, I guess. Thank you.
Questions?
Just to make sure, if you believe Silvio Franz Parisi and Giorgio Parisi, the transition is directly from replica symmetry to full, or there's a 1 RSB phase, or what is this region where they are the same? Does that?
Okay, so there is something like this. So okay, let me remember here. There is here a phase in which so there is a replica. If you look at the volume, so there is a phase where it's replica symmetric, and then when you move up, there is a phase in which there is RSB, and then okay, so it's unclear what happens here, whether and then there is this satisfiability phase transition up there. And now it's unclear whether, I mean, I don't remember exactly, but here there might be an intermediate phase in which is 1 RSB. And then there is what's called a Gardner transition here. Okay, so there is something, so this is the picture.
So it's full above that.
So this is at large kappa, at sufficiently small kappa, some of these phase transition coincide, right? So I don't remember whether these two coincide. But okay, so it's a quite typical kind of phase diagram that you see in constraint satisfaction problems. The difference here is that it is with continuous variables, that make some of the trick that are available with discrete variable unavailable.
Questions?
Yeah, back to the algorithm. So for many of these spin glassy problems, one needs fancy message passing algorithms. But here, is there a feel good explanation for why something simple worked here, like pick a random direction and go in it?
Okay, so what is my intuition why this stupid thing might be perhaps not so bad is what happens in this picture is that if you carve this little, for kappa large negative, you are carving very little balls out of this big ball, right? So if you think now at the energy landscape, this means that this I expect it to be correlated on only very small scales, right? So for very small kappa will be very uncorrelated, and so will be very difficult to make progress. Starting on a position and doing something smart. Now that said, one thing that we did and is that we and I mean Mark and Hamed brought the kind of optimal approximate message passing for it for this problem. This is supposedly give the good, we believe perhaps it gives the right algorithmic threshold. It's not clear how to, at least to me, how to analyze. You get a formula for what is the result that is similar to Parisi formula. It's not easy to compute the asymptotics of that formula for large kappa and see where it falls down in this diagram and compare it. But this is one thing that is.
But the fancy message passing algorithm might do better than 1/8 kappa.
Yeah, it might do better. Yeah, I don't know if it does better asymptotically, right? I don't know, right? I can write a formula, and Dave wrote a formula. you have a, it's a formula, it's written either in terms of a minimization problem over measures or in terms of a stochastic optimal control problem. And then taking the asymptotics for large kappa of this formula is, let's say, future work.
So for that message, for that message, so for the message passing algorithm, these caps, I assume, are the constraint nodes. What are the variable nodes?
No, the variables are the theta, is the vector theta, right? And then
I see. Okay.
And so the message passing algorithm takes basically takes this matrix X with the rows X1 to say that you are in the pure noise, and then proceed by right and left multiplication by X, and then you write an optimal control problem for the functions, and this as a dual that is a Parisi-like formula. And okay, so but it's kind of implicit, so at least analytically it's difficult to say. At least to me at the moment, it's difficult to say a lot about it.
So it's a dense factor graph, but where in some sense the couplings are weak if the things being if kappa is very negative.
Right.
Okay.
Right. You expect that. Yeah, at any given point there is only a small number of them. But
Thanks.
yeah, but otherwise this is very similar to formally to problems that we know how to deal with.
Words about the proof technique? Is it based on Gaussian comparison?
Yeah, so this part is, the analysis of this algorithm is Gaussian comparison.
For the statistical threshold?
The upper bound here is Gaussian comparison, but not in a plain way, because in the plain way it gives you, if you use Gordon inequality, it gives you the replica symmetric formula. So there is a trick there that we do basically we apply Gordon inequality, but not to the obvious quantity. That is so you have to construct a certain quantity, and it's somehow actually it's very nice. And this was a surprise to me that if you apply to the right thing, it gives you this formula that at least to leading order is tight and is a replica symmetry breaking formula, and for the lower bound is kind of weighted second moment method. Yeah, so you have to find the right weighting to make second moment method, and this is the reason why we have positive probability, not high probability. We didn't think a lot of trying to prove a sharp threshold, so that high probability, but that might be within reach.
Okay. Other questions? No?
Yeah, is there any intuition like this log factor in this satisfied?
Sorry?
Like delta SK kappa. So you have this log absolute value of kappa. Is there any way
I
to
don't
see
know.
that?
Okay, there is another way of proving upper bound by chaining. So here it's a bit mysterious, right? In this proof, there is a way to prove this upper bound that eventually will not appear in the paper, but you can. The point is that you cannot use first order method to do upper bound on this because so one way to do it is you look at the process that is the number of unsatisfied constraints, and then you do some chaining for you lower bound the minimum of this, and you do some chaining to lower bound this, and then the log kappa shows up as, I don't remember by whether the number of level, the lowest level in the chaining thing that you have to go to or something like that. In that setting, so you have to take as kappa grows a kind of finer and finer grid. It makes sense, right? What I said before, if kappa grows, if you think of this landscape, this becomes less and less correlated. I mean, the correlation becomes more and shorter range. And so because of that, if you think in terms of chaining, you have to go to a denser and denser grid to make chaining work, right? And if I remember correctly, that is what in that proof make the log kappa appear.
Maybe we can think of the assumption.